graph look for part B?
Unimodal.
Sorry, that was my bad. That was unclear. Just questions about it. Do we agree with it?
Yeah.
Is that what we got?
Well, yeah.
Okay. All right, fantastic. Okay. P.S. I do want to ask, and I want to point this out because this is not a question up here. Is this a true sampling distribution or is this an approximate sampling distribution? Why is this a true sampling distribution, Charlie?
We have all possible combinations.
We have all possible combinations of size 2. So like, please make a note of this to yourself. This is a true sampling distribution. We are not usually going to have that, okay? But that's literally what they had to do, is all combos of n equals 2, size 2, okay? So it's a true sampling distribution. It's going to illustrate something important here. Some people were talking about unimodal. I do like that, right? And we can talk about, if I asked you to analyze it, so remember that's the key language. If I asked you to analyze this distribution, what are you going to do? Cuss in context. Don't forget your context, right? So you can talk about shape. You could talk about the measure of center. You could talk about spread. It doesn't look like we have any unusual features, but that's not the point here. The point is this. What was the mean? And notice the notation I'm using here. You want to hold on to this. What is the mean of sample means? That's how you would read this. This is the population mean of the sample means. Because notice, and I do want to emphasize this, and I might erase one or two of those points if I were you. This point's not just a point. What is that point actually? So if it's 2, it's a sample mean, isn't it? It's the statistic. This is a sample mean. This is a sample mean, right? Those points are not just points. Those points are true statistics. They are each sample values. Star, what did you eat?
Doritos. Drink some water.
Usually those don't make me burp like that. All right. Okay, so you can go through and you can make each value a statistic. So remember, if each dot is a statistic, we're talking about a sampling distribution, not a distribution of a sample, not a population distribution, etc. So what was the mean of all my sample means?
13.3 repeating.
It's 12.8.
How did people get
Check.
13.3? Because Charlie got that and I don't know how.
I just forgot
Something
the
with the
8.
You what?
I just forgot the 8.
You forgot the 8.
Yeah.
So remember, there was already an 8 here. Did you forget your 8? Yeah. That makes sense. So yeah, make sure you include the 8. So 12.8. So I do want to point out, so some people were asking this earlier, like, how am I supposed to calculate this? First, don't forget, there's a formula sheet. The formula sheet tells you the sum of x divided by n, but also if I want to do calculations, what can I always use? List and spreadsheets, the calculator, right? That thing, right? Use that calculator. Your job as a stat student, I need to remind you all this, and I know this is a different way to think about it because we're used to algebra where it's all about the calculations. Your job as a stat student is to recognize what statistics you need to do, and then you use the calculator to do the work. You interpret these things. You make sense of what it means, and so keep that in mind. Okay, so the mean of all my sample means is 12.8. So what was the population mean again?
64/5.
Which is 12.8. So is the sample mean an unbiased estimator?
Yes.
Yes, right?
Where are we getting 5 from?
What does it mean when it's unbiased? That means that the mean of the sample means is what to the population mean?
Equals.
It is equal. Are they exactly the same?
Yep.
So the mean of my sample means is 12.8. The population mean was 12.8. Man, every time I step in front of that projector, I feel like I'm getting blinded. So yeah, the mean of the sample means is equal to the population mean. That is a truth that we see here. So it is unbiased. Remember, I would also remind you, when we say unbiased, that means that it represents the population. Does that number represent the population? Yes. So it's unbiased. Yes, Raina.
So how do you compare with the population? How do you compare with it? Do you average out, you get the mean of just the overall total age?
So sum of all the ages, right? 8 8, 14, 16, 18, divided by 5.
Oh, that was your population mean?
Yeah, that's why I use mu here, not mu sub x bar, just mu. Notice this would be way bigger than 64. Actually, it would be 128 divided by 10. So remember, this was the mean of all these sample means. This was the population mean. It's the mean of the 8, 14, 16, and 18. And those two means are the same. So is the sample mean is what? Unbiased. Okay.
Okay, question.
No answer.
Okay, sorry.
What's your question?
How much like is it? How much lenience is there for like the sample mean equaling the population?
If it's a true sampling distribution, it will 100% equal.
Okay.
If it's an approximate sampling distribution, it'll be really darn close.
Okay.
Okay, part E though, before we go backwards a little bit. So as we had taken samples of size 3 instead of size 2, would the variability of the sampling distribution of the sample mean be larger, smaller, or about the same? About the same is what Raina's thinking.
About the same.
I don't know why, because aren't
adding
there more
random
combinations?
variable.
Okay, so there's more combinations.
Why don't you start with adding random variable and all your consumption variability?
Okay, so let me point this out though. And so we do need to go back and we're going to continue this. Remember over here, we had how many pennies in each sample? We had 5, right? You see the amount of spread right there for those means? Over here, how many pennies did we have?
20.
Is that more spread or less spread? That is less spread. As you're saying, and when we look at the proportions as well, this was still a sample proportion size 5. This was a sample proportion size 20. More or less spread?
It's less.
It's definitely less spread. We're going to learn about rules for why, but as you increase your sample size, the spread's going to what?
Decrease.
It's going to decrease. Here's why. Because yes, there's a lot more going on here, but remember how the true mean was centered, or the mean of this sampling distribution is centered at the true mean? Okay? If I take 20 pennies, and I average those 20 pennies, is it more likely the average of 20 is close to the mean, or that the average of 5 is close to the mean?
20.
The average of 20, like, it's very less likely. Let me say it this way. When I do 5 pennies over there, it's quite possible that I get all 5 pennies in 2010, right? How likely is it I get 20 pennies in 2010? Not very likely.
So more trials.
So a higher sample size does what to the variability?
Decreases
It
it.
decreases it. And it actually ties into what Star was starting to say. What did you say a second ago? The long run probability, right? Remember, if I take more and more samples, aren't I going to approach the true proportion, the true mean, the true population? So like if you take a larger sample size, we're going to decrease the spread of the sampling distribution. Yes, ma'am?
What does it mean by size 2 and size 2?
So remember how we did Erica and Sarah here?
Yeah.
Size 3 would have been maybe Michael, Erica, and Sarah.
Oh, okay.
Yeah. So, but in general, if you increase the size of each sample, then it's going to decrease the spread of the sampling distribution. So I'm going to go back and we're going to cover these ideas here a little bit more cleanly. So this is where we ended yesterday. I think we ended on number 6. Does that sound right?
Yeah.
Yeah. What did we say in number 6? So number 6 says, how do the dot plots for a sample of size 20 compare to the dot plots for a sample of size 5? So is there anything that's the same?
Yeah.
The center. Was the center over there
Yeah.
roughly the same as the center here?
Yeah.
We didn't actually calculate it, but they look about the same, right? Okay?
It's okay.
Yes, sir.
And by measure of century, are you talking about mean?
I mean, does it have to be mean?
No, I mean it could be median, but like,
Okay.
aren't they like a lot of times in this? No, never mind.
I will ask, that actually is a good point. I will say this. Yes, we mean mean in this case. I'll explain why later. But in general, if we say center, what measures of center do we have?
Median and mean.
Median and mean. How different are they in these two sampling distributions?
Not that.
Why are they not?
Because it's
It's
symmetric.
not skewed, it's roughly symmetric, and we're gonna talk more about that, so hold on to that idea. But if our distributions are approximately symmetric, the mean and median are roughly the same, okay? So, the means for n equals 5 and n equals 20 are approximately or roughly the same. But what's different?
Precision.
The spread, the variability, right? What were you saying?
The precision.
The precision. We're gonna come back to that in a second. Yeah. But what has a more precise or less spread? Remember, it's more precise when there's less spread.
A larger sample
A
size.
larger sample size, right? So n equals 20 has less spread. And remember, what's another word for spread?
Standard deviation.
That's a measure of spread,
Variability.
variability.
So can we say, since there are more trials, it is more, the n equals 20 is also more precise?
Be careful, the sampling distribution for n equals 20 is more precise. Because I want you to think about it like n equals 20 can have a lot of spread in just n equals 20, but when I find the average of those 20 pennies, it's going to be close to the mean, the true mean, which is why this spread is so much
How are we
less.
supposed to phrase it?
What do you mean?
So you said be careful about wording, so how?
The sampling distribution. Everything we're talking about, and that's
Oh,
where I talked about.
sampling, oh.
Yeah, so it's the distribution of the sample, the distribution of the population, and the sampling distribution, okay? So you have to be careful with which one we're talking about. So, quick notes, right? So I'm gonna come over to here. So, an unbiased estimator is when the mean of the statistics equals the what? So the mean of all the statistics,
Equals
The population.
population, mean, or it could be proportion. So what is the population value called again?
The parameter.
The parameter. So, you're right that it equals the population mean or the population proportion, but what do we call that in general? That is the,
Parameter.
equals the parameter. Now, so, we're going to explore this more in the future, but what did we say earlier that X bar is supposed to estimate?
The sample mean.
That is the sample mean, but what is it supposed to
The
estimate?
population.
The population
Mean.
mean. Does, we just looked at the check your understanding, does the mean of the sample means equal the population mean? Yes, that means it's a good statistic, it is unbiased. We're going to talk about this more later, but any guesses what the mean of all my sample proportions needs to equal?
The population proportion.
The population proportion, right? The mean of the statistics, my statistic is p hat, right? So what's the parameter for that?
P.
P. So p hat is estimating p, so the mean of the p hats has to equal p. What is S estimating?
Standard deviation.
Well, it is standard deviation, but what's it estimating?
The sample.
The variation.
The spread.
The standard deviation.
Which standard deviation?
The sample. The samples.
The sample.
Yes. Remember, the mean of the statistics equals the parameter. That's my statistic. What's the parameter?
The sigma.
The sigma.
Oh, yeah.
So do you know what the mean of S needs to equal?
The sigma.
It needs to equal
The mean of sigma?
not the mean of sigma,
The sigma.
the sigma. Remember, the mean of the statistics needs to equal the parameter. Okay? Now, I'm gonna take a second here, and this is not a part of this, but it helps explain some things, and I want y'all to see this. Do you remember that there was actually two different formulas for S versus sigma? S was the square root of the sum of my values minus the mean squared divided by n minus 1.
But then that one was just N.
But for sigma, it was just n.
Because we have a census.
Well, when you have a census. But here is the reason why. If I do this formula right here, the mean of those sample standard deviations does not equal the population standard deviation. This is an adjustment we found in statistics that we needed to make it unbiased. Okay? And I'll explain why in a second. But if you use this formula, so if we had let S equal this, these two things would not be equal. Okay? So if we let S equal this with just an n and not the n minus 1, these would no longer be equal because S would be a biased estimator. What we found was, if we make this adjustment n minus 1, then we are getting an unbiased estimator, so it works now. Okay? So we had to do n minus 1 to make it unbiased. The reason why is this: how likely is it that you get the most extreme values on a graph? Not very likely that you get the most extreme values. There's one penny at 1951. I don't know if anybody got that, right? It's not very likely you get it. But notice, if I take the number 20 and I divide it by 5, what do I get? 4, okay? But let's say I subtract 1 from that 5 and I divide by 4, what do I get?
4, 5.
5. When I divide by a smaller number, it increases the spread, and it accounts for the fact that I didn't get the most extreme values, okay? So when I divide by a smaller number, like by 4, it increases the measure of spread, accounting for the fact that I don't get the most extreme values. That's actually why, so you may be asking, okay, so what's a bad estimator? Range. If I take the sample range, and I do the mean of my sample ranges, it will never equal the population range. It just won't. Okay, so if I take the mean of all my sample ranges and I find that mean, it'll never equal the population range because the population range is usually going to be bigger than any sample. Okay, and so there are lots of estimators out there that we don't use. Anyone know another? Yeah, median. That's what I was actually going to say. Another statistic that is biased is the median. If I do the mean of my medians, it does not equal my population median. So these are all biased estimators. That's why we don't use it in what we study later. Because if you remember, at least the question I have early is, why don't we just use median if it's not affected by skewness? We don't use medians because it's a biased estimator. Okay, we don't use medians because they're biased estimators. Okay. So, biased is when the mean of the statistics equals the parameter. Can I erase this part so I can get to the variability side?
Well, yes.
Okay. Alright, so the variability side is the precision. So that's the accuracy, right? So we think accuracy over here. Oops. Here is the precision. And what we found is as n, what is n again?
The
Number of trials.
So the number of trial, be careful. So it's the size of each trial. Yeah, so as n, this is the sample size of each trial increases. What happens? The spread, what? Decreases. So what do we call that? It becomes more precise.
precision.
Now, precision without accuracy is not super useful. Okay? So precision without accuracy is not very useful. So we have to have an unbiased estimator first, and then we increase our sample size to decrease that spread. We have to have an unbiased estimator first. Then we increase our sample size to decrease that spread. And we're going to learn eventually about what a good sample size is. Okay. But just be aware, principle right now is, as the sample size increases, our spread what? Decreases. As the sample size increases, spread decreases.
So precision doesn't matter if it's not.
Precision doesn't, yeah, precision's not helpful if it's not accurate. That's a good way to think about it. All right. So this is off an old set of notes, and I just kind of left it in here. So again, in general, how can you reduce the variability of a statistic? You need to what? Increase the sample size. Yep. Got to do it. Okay. And then what's the difference between accuracy and precision? We already talked about that. So accuracy means it's centered around the mean. Precision means it has low spread. All right, Star. You know what's about to happen? It's your favorite lesson.
No.
It's the one you've been waiting for.
No.
Yeah, it is. So we're going to have to go back to some probability. But it's time for lesson 6.7. He's hype. All right. Got him engaged. So what we're about to learn about, this is one of the things that we didn't learn in the probability unit, part 2. It will not be on your test, but it's very important for what we're about to do. And so we're going to do an abbreviated version of this. Okay, so we're going to talk about something called 10% condition and large counts. And so we're also going to learn right here, when is it appropriate to use a normal distribution when we don't know what the distribution actually is. Okay, and so it's going to tie into this of when a sample proportion can be approximately normal. All right, so 6.7, do you like green Skittles?
No, I like the red bag.
Well, does anyone remember when they changed the green Skittles?
So lime?
Yeah.
I love the sour green apple.
Me
I'm
too.
not
I do
gonna
too.
lie. I love green apple. All right, anyways, but I think they went back to lime. So like it was lime, and then they changed it from sour apple back to lime. I don't remember, something like that.
Super sour pack?
Yes, don't, yeah, anyways.
They don't sell.
Alright, so right here in 2021, Skittles changed the flavor of green from sour apple back to lime. Mr. Wilcox, who is the one who developed Mathematic, takes a small handful of 5 Skittles from a bin of 10,000 Skittles and gets all green. If 20% of the Skittles are green, what is the probability of this happening? So first off, just take 30 seconds, talk with your group. Is this a binomial set? Well, yeah, it is a success of all green, but is it binomial in general? So like, what do you need to check to see if it's binomial?
But is it not first set?
I wrote not a
Yeah, it's a binomial set because it can either be green.
I'm next.
Let me log in.
So,
I mean, I guess I can
Okay,
use
taking more than one out, It'd be full.
But it's not currently.
Alright, so there's our 30 seconds, let's talk about it. So, a lot of our groups, we realize we gotta check what to make it binomial. Bins. Remember, for your test tomorrow, one of the first things you need to think about anytime you're dealing with probability for the rest of this class, for the AP exam, if you see probability, you need to check, hey, is this binomial, right? So is it binary?
Yes.
Okay, what are the two situations? Either you get green or you don't get green, okay? So it's binary. Independent trials.
yes.
No.
You're
Okay.
replacing.
Say that one more time.
Replacing because you're taking your 5 and you're putting it back.
But
It's a handful.
you're taking a handful, right?
Yeah, which means you have 5 out at the same time. It's not. There's no replacement going on.
If there was replacement, right, one draw would not affect the next draw, but he just takes all 5, right? So they're all at the same time. So is the one Skittle independent of the next Skittle if he draws all 5 of them at the same time?
No.
No.
They're not independent. Okay, is it a fixed number of trials?
Yes.
And it's 5 Skittles, right? Overall, is it the same probability each time? Well,
No,
Yeah.
it's not, like.
The probability of a Skittle being green is 20%. Why are we thinking not really, Madeline?
Because like, if you draw a red one out of all of those, then it changes. Just
It
a
does
fact.
slightly change the probability, and so I'm okay with you saying it that way or thinking about it that way, totally fine. The bigger thing is, they're not independent, I'm drawing them all at once, okay?
How?
Well, I'm not drawing one and then putting it back. If I drew one and then put it back, the second Skittle isn't affected by the first Skittle, right?
Wait, so like he's just drawing 5 and then drawing
Right, that's what it says, he grabs a handful of 5 Skittles, so they're related to each other, right? They're not,
Yeah, because the same as
Yeah,
the
because-
five.
Yeah.
Can we say no?
And then he picks
so there's
the
no
number 5.
replacement, that's the big thing here, we're gonna talk about that soon, right?
Sample is five.
No replacement.
Oh,
If there was replacement, which I need to remember this when I talk about this for the first unit in the future. Remember how we talked about sampling with replacement and without replacement?
Yes.
Yeah.
Okay, sampling without replacement means that the first selection affects the next selection.
Yeah.
But if I put a person back and I can select them a second time, those are independent events. Okay, so the no replacement here means that these are not independent events. Okay, so what I want you to do is take another 30 seconds, talk with each other. How are we going to find the probability of getting 5 green Skittles if this is not binomial?
Did you measure first failure at
It's not, and so it's not independent. But so let me ask you this: the first Skittle, what's the probability of the first Skittle is green?
Because
Now it's 20%, right? So it is 0.2. Think about it as a relative frequency idea. If 20% of 10,000 Skittles are green, how many green Skittles are there? 2,000 out of my 10,000. But then the next Skittle wouldn't have that same exact probability anymore, which is what you were thinking about with
yeah, it's just
that idea.
check one and
I
try.
suppose not the 0.2.
like 0.2?
I would not, nope, can't do 0.2.
Oh yeah, wait, no, wait, it would be 0.2.
Because remember, they're not independent.
Yeah,
It's not
The
binary.
denominator changes too.
I'm just kidding. That's still your idea.
So it would be,
Well, yes.
Would it be that? Because if you take a green Skittle out, right? So like we had 2,000 out of those 10,000 Skittles were green, right? But if you take one of those Skittles out, how many green Skittles do you have left?
Oh, wait, no.
because from
1999.
1999. And how many total Skittles are there?
10,000.
How many total Skittles?
9,000.
9,999. Notice that's not exactly 0.2 anymore, is it?
Oh, yeah, never mind. Okay, so then it is just 2.
Okay?
Yeah.
Alright, so bring it back together. So notice, this is the idea of the first green and the second green and the third green, but really the second one being green, that's the probability of the second being green given the first is green. I'm not going to do this all the way through, but if the first one is green, how many green Skittles do we have left? Remember, there's how many green Skittles in the whole thing?
1999.
So there's originally 2,000 green Skittles. I've taken one out, so now I'm left with 1999. How many total Skittles are left if I've taken one green out?
9,999.
Okay, so that's probability of the first Skittle being green. The second one
1998.
times 1998
19,998.
1997 divided by 9,997 times 1996 divided by 9,996. Whew! Multiply it out. I think you already got that though, didn't you, Madeline?
That's like 3 trillion.
So there's my work. What's that equal to?
0.00318.
Was it 2 zeros or 3 zeros?
3 zeros.
3 zeros, 318?
I understand.
Yes.
Okay.
Um,
Those are not independent events. Okay? Say that one more time. Right, because we took one out each time, right? So one green, so now we only have this many green. Took out another green, so we only have this many green. And that's it, right? So there's my probability. Now, work on numbers 3 and 4. Notice in number 3 it says the find the probability of getting 5 green Skittles if this were a binomial setting. Write out your formula, practice writing out that formula, and do the calculations in the calculator, please. Yes. But is it geometric or binomial? So we don't want geometric. So try, we said binomial, didn't we? That's what it says right there. Because it's not, remember geometric is the first success. So we don't want the first success, and also it's not 0.8, it was 0.2, wasn't it? But geometric is the idea of the first success. I'm not looking at first success, I'm looking at 5 successes in 5 trials.
Hey, what was the order to put the values in for this again?
N is, remember, your number of trials, R is your number of successes. But remember, the calculator can do the whole binomial for you. You can do that if you want. What's your question, Madeline?
I'm just trying to write it out, I got that.
Remember, you have a formula sheet,
Something. Well,
right?
is that, I don't remember which number.
But so what does N stand for? Lowercase n, and especially in binomial, is your number of trials. So number of trials. So notice it says,
So
with,
it's just,
it just says n. So number of trials and number of successes. How many trials are you doing? Not 10,000.
1999.
You're only doing 5 trials, right? 5 Skittles? Okay. Yes, sir.
Okay, I was just confused why you wrote the notation on the side, but you wrote it over there.
This right here,
Yes.
this was showing that the probability of the second being green, given the first is green, is not 0.2 still.
Okay.
I'm just showing like that probability is changing.
And for that,
And that's how we got this.
that's not all of it though, right?
Well, that's all of it if I'm doing 5 Skittles. 1, 2, 3, 4, 5 Skittles,
Oh, okay.
right? Okay, so probability that x equals 5. So remember, and I'm glad that I asked you to write out this formula. So first off, what is the binomial formula? N choose x times the probability of success to the x, the number of successes, times,
1 minus p.
what is 1 minus p? Don't forget what it really means.
Probability of failure.
Probability of failure raised to the number of failures, right? So, yeah. You can do that. Okay. So what does this N stand for again? That's the number of trials. How many trials do we have? 5. How many successes do we have? 5. Probability of success is 0.2 to the 5th times 0.8 to the 0. When you put that into the calculator, remember, just go to binomial distribution. You can do it that way as well, where you do the individual pieces. But if you go to binomial distribution, what probability do you get here? 0.00032. We'll take up there after lunch. Yes.
I need to memorize the binomial because I don't remember it. Yeah, true, but I don't
So
feel like,
N
because
is the number of
I
trials.
can look at it, but I don't know what to plug in.
Yeah.
But, because I need to memorize what each, like, number means. Like, N minus X, what does that mean?
So basically, number 2 is wrong.
So
Oh, it's
make
not.
sure you
It's like it's
copy
approximate. It's not
this.
precise.
That was listed 6566. It's not 10,000 trials. First of all, that can't. Okay, so number 4 just simply asks the question: how do your answers from numbers 2 and 3 compare? How
Almost
does
no difference.
Huh?
Almost minute difference.
So minute difference. So effectively the
Almost correct.
same.
Almost the same.
Why is it effectively the same? Like these weren't independent events, so why in the world, like notice the probability changed each time, so why was it effectively the same?
It's a lot of Skittles.
There's a lot of Skittles, right? Okay, we can get more precise with it than that. Charlie?
Has the difference of one schedule that doesn't really affect the odds that much?
Okay, so it's not just that there's a lot of Skittles, the difference between the number of total Skittles and the number of green Skittles is so different, right? Okay, so that's a big part of it. And notice the probabilities don't change that much. There's a term for this, I feel like.
Ooh,
I wonder where we might be able to find that term.
We get it.
Large count condition,
Or
I don't know what the 10% condition is.
10% condition is the one I'm looking for. Okay?
Well, it's 10%.
I'll talk about large counts in a second. But look, my sample size
Oh, this one.
is less than 10% of the population size. Okay? This is showing that if our sample size is less than 10% of the population size, remember, how many Skittles were we looking at?
10,000.
10,000, right? We only grabbed how many? 5. So did one Skittle really affect the probability of the next Skittle?
No.
No. So when your sample size, when sample size is less than 10% of population size, when this is true, we can treat trials as independent. This 10% condition is going to show up in every single inferential procedure we do from here till the end of AP Stats. You need to check your 10% condition on everything. So go ahead and make sure you know this. If your sample size is less than 10% of your population size, they're not independent events, but you can treat them as independent. Specifically, I will say, I should have added this detail, can treat trials without replacement. Because if you use sample with replacement, they are already independent. Right? If you sample with replacement, they're already independent. But if you're doing it without replacement, which is usually what we do, because I don't want to select Madeline 5 times to figure out what her favorite candy is, right? If I want to find out the favorite, I know because they're the best, I'm with you, right? But if I want to know the favorite candy of everybody at the school, just Madeline's not going to give me a picture of the entire school, right? So we always sample without replacement. So if we have the 10% condition, which, sorry, I should write that here. This is known as the what? 10% condition. Then we can sample without replacement and treat our trials as independent. Okay, so 10% condition. All right. Any questions about that concept? No. I'll take that as a no.
Wait, how would this?
Why do we do that?
What?
Why do we do
So remember, so here's the thing. Doing this, and we're actually going to talk about something else in a second. We had to think through the work of figuring out how many Skittles there were to how many total Skittles or green to total each time here. Whereas if I had just done a binomial from the beginning, it's way less work. So, but in order to do binomial, we had to have independent trials, and we didn't originally. So if we want independence, which almost all of probability is built on independence, then our sample size needs to be less than 10% of our population size. So like, if we want independence, we can use the 10% condition. Thank you. Who's that from? Huh? No, I'm teaching. You can interview me after this class. No, I'm teaching. You can interview me after this class. Also, is this the same question that Malia just asked me? What was that?
Oh my God.
Well, Malia was asking me if I knew why the seasons are the seasons on Earth. I think it's for whatever.
Earth and space science?
My guess is Earth and space science to see if teachers know.
It's because of the tilt of the axis. That's like basic.
Yeah, that's it. Yeah. All right, guys, we gotta get back to the stats though. Yes, Ian.
When would a sample be less than 10% of the population?
Well, I mean, how many Skittles did we have here?
10.
Wait, 10,000. How many Skittles did we select?
5.
Is that less than 10% of 10,000?
Well, yes.
Okay.
Okay.
If I had chosen, say, 2,000 Skittles, then that would not be satisfying the 10% condition. Because 2,000 is 20%.
Yeah.
So the sample size has to be less than 10% of the population size.
What if
By the way, I meant to mention this when y'all first came back, because I noticed some of us are struggling with the number of trials in a binomial. Remember, the number of trials is how many times you do a thing. How many times did you draw a skittle?
like 5 times?
5 times. Notice, because I think some of us were originally thinking 10,000 skittles. We did not do something 10,000 times. The number of trials is how many actions were taken. And then X is the number of successes. Yes, Phoebe.
Okay, so for the 10% condition, if it's like exactly at 10%, would it satisfy it? Like, same with the statistical significance?
It does say less than 10%, so I'm going to go with strictly less than. However, how likely is it, do you think, that they're going to give you that, like, right on? They're not going to.
Yeah.
Don't sweat that. Just think less than 10%. Okay. So here's something I'm going to walk us through and I'm going to do with y'all because the next part of it, of the 6.7, I don't love the way they have it set up on here. This is based on an activity, I think it might be in the book. I know I got this from Josh Tabor, who wrote our book. This is going to explain the large counts condition, Madeline, that you were talking about. Okay? So we're actually going to use the Candy Machine applet for another activity in a second. But here it is. This is the Rossman Chance applet collection. And I just want to go on record and say, Reese's Pieces are garbage, but Reese's are awesome.
What's that?
The Reese's Pieces are like the Reese's version of M&M's.
I've never tried it.
Straight garbage. Don't. You're good. Huh?
It's like too
Yeah.
small.
Anyways, but that's what this applet is based on. So right here, okay? So here's what we're going to do. So I want y'all to investigate and see what happens in a second. So right now, I'm doing a sample size of 25 and 10% of the Reese's are orange. So we're going to look at this. So it's probability of orange was 0.1 and we're doing a sample size of 25, right? And I'm going to do 1,000 samples. Any prediction what my histogram will look like for those number of orange Reese's Pieces?
Skewed to the left.
Skewed to the left? Any other thoughts? Normal maybe?
I don't know.
Let me ask you this. I'm going to pose this in a second. Okay, if the probability of orange is 0.1 and the number of candies I'm selecting is 25, what number of orange do you expect to see?
3.
I wouldn't say 3, but you're close.
Well, yeah, 2.5 mil from me. Oh, 2.5.
2.5. Where's the 2.5 coming from?
10% of 25.
Well, so the probability is 0.1, right? Notice this is a binomial setting, isn't it? And when I say the word expected, you should also think of what word? The mean, right? So the mean number of Reese's Pieces that we should expect to see is 2.5, n times p. So, but then if I'm selecting 25 candies, how many orange could be, or how many candies could be orange?
25.
25, right? So think about that logic. Notice, what's the shape?
You skewed right.
Skewed right, because it is centered at what value? 2.5, right? But then it could have more than that, can it? So it is skewing to the right. Okay, so the next option is n equals 25 and p equals 0.5. Alright, so I'm going to do this again. And draw those samples. Notice what's that shape?
Symmetric.
It is roughly symmetric, right? Because how many do we expect to see? 12.5, but it could be some less and some more, right? Okay, let's look at the next option. I'll draw this up there in a second. N equals 25, and the probability of getting an orange is 0.9. Any guesses on this?
Skewed to the left.
Skewed left. Okay, why do you think it's skewed left?
Because you could have some that's less than.
Right, so I would expect actually 22.5, 0.9 times 25. But then I could get some significantly less. So it is skewed to the left. Okay, so what we have so far skewed right, approximately symmetric, skewed left. And remember we said the expected number of orange was 2.5. The expected number of orange was 12.5, and the expected number of orange is 22.5. Okay? What do you think is going to happen here?
Skewed to the right.
Skew to the right? Okay.
That's where it's you could write out the volume increases.
Let's find out.
There's a probability.
Oh wait,
So
but
we're gonna do
our sample size
100?
is increasing, so the spread's gonna be less.
And then it's gonna be 0.1. What does it look like to you?
Symmetry. Because our sample size is increasing, so the
Oh, that's right, our sample size is much larger this time, isn't it?
I guess.
Okay, and so it's 0.1, so it's probability, so we expect to see 10, right? Which seems to be the middle here, but we could get some less, we could definitely get some, or some more and some less, okay?
But it's still a little, like, would you say it's still a little skewed left? Or you skewed right?
I could say maybe a little skewed right, maybe a little bit skewed right, but not much at all, that's roughly symmetric. And so, this is the next one. How would you describe that?
symmetric.
Roughly symmetric. There's another term I feel like we could use here. Not, it is unimodal, it's roughly symmetric, so it's approximately normal. Okay,
Just normal.
so, coming back to here. What is the expected number in this case?
10,
Okay, what's the expected number in this case?
50,
And the expected number here?
90.
Okay, now, I'm going to pause for a second. I'm going to point this out. This was 22.5 orange is what we expected. So how many did we expect to not be orange?
2.5.
So when do we get the distribution to be approximately normal? When what? So when the sample is larger, right? But notice it didn't have to be a very large sample here.
The probability just had to be 0.5.
The probability in that case had to be 0.5. I will say this, if you do n equals 25 and a p of 0.2, that would also be approximately normal. Any guesses as to why? How many Reese's or orange Reese's would we expect there?
Oh, 5.
No.
What?
Did I do that wrong? I did that wrong.
So-
You're right.
Wait.
That's not the number I meant to do. Meant to make this 50. Sorry, and that 0.2. That would be approximately normal.
That'd be 10.
That'd be 10. So notice it doesn't have to be super large for the sample size. Could just be 50.
Is it a relationship between N and P?
Okay, so there is a relationship between n and p because it's either orange or it's not, right? So this is binomial, right? And so isn't the mean just n times p? Like, that's how we calculate the mean for a binomial random variable. But notice here is approximately normal, here is approximately normal, approximately normal, approximately normal, but not here. What's the key number I got to on this one?
0.2. 10.
10. So what we will see, and we'll see this more often, I want you to go ahead and start holding on to this, and we see in the next lesson heavily, is this. This is known as what condition?
10%?
We already did 10%. Large counts condition. And so I'm going to write this in the mathy way in a second, but I want you to go ahead and make a note of this. Bless you. Number of expected successes is greater than or equal to what? Think about the numbers I've given you so far. What was the lowest threshold? Someone said it.
50%.
10.
Yes. Let's go.
If the number of expected successes is greater than or equal to 10, then it's going to be approximately normal. Except that's not always the case. Does anyone see one of the cases up here where we had the number of expected successes greater than or equal to 10 and it still wasn't approximately normal? The top right, number 3, right? Any guesses why?
Because the sample size is too small.
Not just that.
Sorry, I don't know how to voice it.
Say again.
Sorry, I don't really know how to voice it, but it's something to do with like, and like you're expecting the opposite of, and that.
Yeah, so what would be the opposite of successes?
Not-
Failures. So we need the number of expected successes to be greater than or equal to 10, but we also need the expected number of failures. So number of expected failures is greater than or equal to 10. If both of these are true, a binomial random variable is approximately normal. If both the number of expected successes and the number of expected failures is greater than or equal to 10, the binomial random variable is approximately normal. Okay? And that's what we saw with the Reese's Pieces. And I'll show you some more in a second. But this is another one. You need to go ahead and hold on to this name, because if you're ever dealing with proportions, you need to check the large counts condition. If you're ever dealing with proportions or a binomial situation, you need to check large counts. What I will point out is, look over at the pennies. When n equals 5, it's not quite normal, is it? It looks more kind of skewed left. But now look over here. When n equals 20. Still a little skewed left, but what does it look much closer to?
Symmetric.
Looks much more symmetric, so approximately normal. The large counts condition is something we're going to have to hold on to heavily for the rest of AP stats. Anytime you're dealing with proportions, you need to think about large counts. So, notice, I'm going to show you, I'm going to erase some of these graphs real quick and leave that over there. But notice if I do n equals 50 and I do a probability of 0.1, what's n times p there?
5.
5 is, so should this be approximately normal?
No.
No. So let's check it though. What is that? Skewed right. It's not super skewed right, but it's definitely skewed right. What about if I did 50 and 0.9? Should that be skewed or approximately normal?
Skewed.
Skewed left, because what would be the expected number of failures? Well, expected number of failures.
Oh, like
Would be
5.
5, right? That's less than 10, isn't it? Okay, so let's see. Yep, skewed left.
Yeah.
But what if I make this 0.2? What is 50 times 0.2? 10? So it should be approximately normal?
Yes.
Is that what we see? Not perfectly normal, but it's definitely much more normal than what we just saw. So if the large counts condition is satisfied, that distribution would be approximately normal. Okay? Alright, so let's go ahead, I'm going to come back to this to give you all some practice with it, but I want us to go ahead and get our notes here, our quick notes. Let's actually just go ahead and put this under large counts. So on the right hand side, you got your large counts condition, that's what I wrote over there. So put large counts in there. So if this is true, a binomial random variable is approximately normal. So if those statements are both true, a binomial random variable is approximately normal. And what is this rule called?
Large counts
It's
condition.
my large counts condition. That is large counts.
So when you say expect this failures, doesn't mean
Say again.
when you say expected the success of failures.
That's a good point. Actually, yeah, let's add that detail. How do we calculate the expected number of successes?
The trials and the,
Yeah, that is a greater than or equal to. I accidentally started to erase it, my bad. It is greater than or equal to. So, Star, what were you saying? Number of trials times? So, probability of success needs to be greater than or equal to. So how would I say the number of expected failures? How would I calculate that?
Number times P minus 1 minus P, or times, yeah.
So this is the mathy way to do it. That's what you really need to check. But this is what it means. The number of expected successes, that's n times P. The number of expected failures, that's n times 1 minus P. Both of those need to be greater than or equal to 10. If that is true, binomial random variable is approximately normal.
Is that the same thing as saying like P complement?
Yes. But be careful because we put complement on the event. We don't put the complement on the probability. P is the probability. Okay? So, again, this is the mathy formula way to say it. That's what it actually means. Pair the meaning with the formula. It'll make things much easier. All right, 10% condition though. What does N stand for again?
Number of trials.
The number of trials, the sample size within the trials. But that's my sample size. If that sample size is 10% of the, what's that big N?
The population.
Population size, there you go. If my sample size is less than, is what in respect to 10% of the population size? Okay, so if sample size is less, then the what?
Binomial.
You can consider as
Oh.
independent.
The trials can be considered independent even without replacement. So if you replace your selection each time, it's already independent. But if you don't replace, 10% condition allows you to treat the trials as independent, or the samples selected. So once you're done with those quick notes, flip it back over. I do want you to work on number 5 through 8. I'm going to give y'all a few minutes. Not sure exactly how many yet. Okay. I will point out in numbers 5 through 8, just to keep this in mind, what type of random variable did we decide we have since we do have independent trials? 1 through 4, we said, okay, we can treat this as independent trials. So what type of random variable do we have? We have a binomial. So when it starts asking about the probability, remember you have a binomial random variable. When it starts talking about the mean and the standard deviation, do we have a way to calculate the mean and the standard deviation in a binomial random variable? Yes. Where can we find that?
Formula.
Formula sheet. Okay, you got 5-ish minutes. Work on 5 through 8, then we'll come back and we'll talk about 5 through 8. 6.7. Yes. Yes.
Yes.
What? What's the question?
Yes.
Wait, what's the question?
I thought,
5 through 8 here.
yeah, hold on.
No, here.
Oh.
Just those 4 questions, real quickly. So at 119.
Yeah, I have to ask Ruby.
5 through 8.
You know what? Please.
TV. I have to get a close enough approximation?
Yes.
Sure. Now, does anyone else asking the question why in the world? Huh?
So really do have to use the negative.
Yes,
Yeah.
I think. Yes, I rounded. Is anyone else wondering why in the world would I go through all this work of converting this to a normal distribution when we could have done binomial random variable?
Because statisticians like it.
So statisticians do like it. We can do it because of large counts, but why would we care about this? One,
It's a demonstration that you like. That's how you can use it.
So two things, I mean, you're not wrong, but two things. One, this is gonna be useful for when we do inferential procedures later. So there's a concept that we haven't studied yet that you need to know in normal distributions and that you can use in normal here. Second, y'all, calculators like this are a brand new concept. Like in the world of statistics, the world of mathematics, calculators like this are brand new. You couldn't do binomial random variable in a calculator until fairly recently.
What?
Yeah, that's crazy to think about. But they've always had normal distribution tables. So the normal distribution approximation was easier 20 years ago.
But you're telling me they had to write all these out?
Yeah, if you want to do a random variable like this, yeah, that's the thing. Like, would you ever do a random variable by hand with 100 Skittles? Hard pass, right? You would have had to write it all the way out. So a normal distribution 20 years ago, 30 years ago would have been much, much easier. You don't need that today.
What is large challenge?
It was discovered.
So the.
Great question.
So did you do it by hand on your test?
That.
Not that old!
What was it like going to school with dinosaurs?
Alright, hey, we gotta continue. Kenji, what you got?
Where did you get the 0.0122 from?
That's what people told me. I'm assuming they put normal distribution in their calculator, and they did a lower bound of negative infinity, so like negative 100, upper bound of that, and that's the area that they got.
Wait, why wouldn't you?
So remember, we just said, hey, it's a normal distribution, so I'm doing normal
Why wouldn't you
CDF.
do your upper bound as 11?
Because remember, we converted to a z-score.
Oh, well, yes.
So where the mean is 0, standard deviation is 1. Okay. So I do want to point out, I got to continue here, but I do want to point this out. Please notice, the stuff that we learned in Unit 2 hasn't gone away. No. We're going to continue practicing with normal distributions. We're going to continue practicing with analyzing distributions. My point is, once again, I know that stats and AP class in general, but especially AP stats can be tough, but you're going to have lots of opportunities to master these ideas. I don't care when you learn it. If you care that, you learn it. If you have a C and you want an A, you can still earn it. If you have a B and you want an A, you can still earn it. You got a 95 and you want 100, you can still earn it. Because I'm going to get those proficiency scales to you ASAP, I promise. And then we will work on updating your knowledge on things I didn't see evidence with. I'll get it to you this week, I promise. Alright, so we got to check your understanding. I do want to start the next lesson. So I'm going to leave this check your understanding for you to work through, to think about first, figure out what questions you need to ask. I don't know what that symbol is, but sure. Oh my gosh. Moving on from Star's favorite. Sorry, buddy. We're going to continue with the idea of the 10% condition, the large counts condition, and talk about normal distributions again, but this is still within the sampling distribution stuff. So most of the foundations for sampling distributions we should have down by now. And we're going to discover the parameters of sampling distributions for proportions. Okay. So, going back to Reese's Pieces. Okay? So, we're going to work through this. We're mostly going to kind of have to start this all together. But Reese's Pieces, what was the probability of orange on there? Was it point? So, by the way, this is 7.3. Okay, so we're going all the way to 7.3. Okay. Dude, I love Reese's Puffs, man. That speaks to my childhood.
Those are disgusting.
You're disgusting. Sorry, it's a visceral reaction. I love Reese's Puffs. All right, what's the probability of orange?
Point something.
It's on there.
I'm not there yet.
Does it say 0.4?
0.4.
What's my number of candies?
50.
50, and then 1,000. Oh, so yeah. So let x equal the number of orange candies in the sample. Explain why x is a binomial random variable. What can we write there?
Because this.
Wait, what?
Bins. Okay?
What are Reese's Puffs?
It's a Reese's cereal. Okay? Is it binary?
Yes.
So it is orange or not. Okay?
I'm sorry, Alex.
If I'm drawing Reese's out, do we have independent trials?
Yes. No.
Oh.
No, you don't.
Why not? Because you're doing it without replacement.
But it does
But
follow the 10%.
oh, but it does satisfy 10% because how many Reese's are we drawing out?
One each time?
Less than 10%.
Less than 10%?
What, how many? We're drawing out 50. And how many Reese's Pieces are there?
1,000.
1,000. So 50, and this is what you would need to check. You need to recognize this is not actually independent, but is 50 less than 10% of 1,000?
Yeah.
So can we treat these as independent? Yes. That's the point of 10%. It's not actually binomial, but I can treat it as binomial because we've satisfied the 10% condition. Okay? Do we have a fixed number of trials?
Yeah.
Yeah.
What is the number of trials here?
50.
50. We're drawing 50 out. So n equals 50. Same probability of success. Yes. P equals 0.4. Yep. All right. Can we treat it as binomial?
Yes.
Heck yeah. Sweet. That's useful. All right. So,
Wait, so what do you call the things that you, the cup? Oh, cups? Reese's cups?
oh, Reese's Cups are what it's at. That's what Madeline and I were
Oh.
fangirling over earlier.
They made me sick.
Okay. What?
Well, not really. I just made that up.
Did you like those lights that on this?
I will help you earn those points otherwise. All right. So, here's what I need you to do tonight. I know y'all have a test to study for, but yeah. So this. No. You have a test tomorrow. Did
Friday, I said Friday.
I just say test Friday?
No, you said Thursday. Wait, oh wait,
Friday.
wait, y'all lying?
Yeah,
No, you
test
said Friday.
Ian, DYU on Friday.
It was Friday.
He said
The
test
probability
Friday.
is that we haven't taken the test
You
on
said
yet.
test Thursday.
Yeah. Okay. So, yes. Okay. So remember, I do have a Mu Alpha Theta meeting in the morning, but I will definitely be here early.
Tomorrow
Hold on.
morning?
Yeah. There's an option tomorrow morning, and then Jaden picked Friday afternoon.
Yeah.
But I will be here in the morning to answer questions. If you come in and you want to ask about statistics, I will answer those questions before I do Mu Alpha Theta stuff, and I'll be here first block. But what I need you to do is I actually need you to do, this is super simple, so you can do it. I just need you to draw 5 samples. So like right now, how many orange candies did I just get? 24. And put it here. I'm going to do this a second time. And now I got 24. Okay, and a third time, fourth time,
18.
and fifth time.
24.
I want y'all to do this on your own, draw 5 this way, and we're going to create a dot plot out of all of the class's draws, okay? There's a reason why we're going to want to do this, okay? So, tonight, make sure that you complete, hey guys, right here, tonight, make sure you do numbers 2 and 3, and actually, you should be able to do at least 2 through 4, okay? So should take just a couple minutes. We'll pick up there tomorrow after the test. So the test will be before lunch, and then we'll finish this lesson up after lunch.
What's our test on? Like,
Probability part 2.
What's the call?
It's combining random variables, transforming random variables, binomial random variables, geometric random variables, and discrete random variables. Oh, and continuous random variables.
wait.
It's the proficiency
Wait,
scale.
Mr. Kenny, okay, so, well, say I had a test tomorrow, like, what should I do tonight?
I would start maybe with, like, I can reopen the progress checks if you want to work back through it and see what you need to work on. I'll reopen the progress
I'll give you
checks.
the one that I've been using as I've been using one as a.
I'm just so bad at progress.
But hey, don't forget you have a progress check for safety distributions as well.
Oh, and tell me which classes
You wanna make the classes too? Just three classes.
We gotta go find the advanced.
But they don't have options.
Okay, right now.
Let's not do that.
Already
I'm just gonna go to like every class. Maybe I'll go to the office.
Oh, Mr. Asmus.
Probably, yeah.
The one by himself.
But you have